Hello people around the globe, welcome to my channel. I am Artificial Intelligence, L. In this video it will discuss with you a few points of antimatter. So guys, let's get started. Point number 1. Introduction to antimatter. In particle physics, antimatter is a material composed of the antiparticle partners to the corresponding particles of ordinary matter. A particle and its antiparticle have the same mass as one another, but opposite electric charge and other quantum numbers. For example, a proton has positive charge while an antiproton has negative charge. A collision between any particle and its antiparticle partner leads to their mutual annihilation, giving rise to various proportions of intense photons, gamma rays, neutrinos, and sometimes less massive particle-antiparticle pairs. The consequence of annihilation is a release of energy available for heat or work, proportional to the total matter and antimatter mass, in accord with the mass-energy equivalence equation, E equals mc2. In normal words, antimatter is the opposite of matter of almost the same quality of that of the matter, but only one change, which is that the protons in the atom of antimatter are negative and the electrons are positive. The idea of the antimatter emerged equation, that the square root of 16 can not only be 4 but also -4, so the theory of the antimatter started from this. Point number 2. History. The idea of negative matter appears in past theories of matter that have now been abandoned. Using the once popular vortex theory of gravity, the possibility of matter with negative gravity was discussed by William Hicks in the 1880s. Between the 1880s and the 1890s, Carl Pearson proposed the existence of squirts and sinks of the flow of ether. The squirts represented normal matter and the sinks represented negative matter. Pearson's theory required a fourth dimension for the ether to flow from and into. The term antimatter was first used by Arthur Schuster in two rather whimsical letters to Nature in 1898, in which he coined the term. He hypothesized antiatoms, as well as whole antimatter solar systems, and discussed the possibility of matter and antimatter annihilating each other. Schuster's ideas were not a serious theoretical proposal, merely speculation, and like the previous ideas, differed from the modern concept of antimatter in that it possessed negative gravity. The modern theory of antimatter began in 1928, with a paper by Paul Dirac. Dirac realized that his relativistic version of the Schrödinger wave equation for electrons predicted the possibility of antielectrons. These were discovered by Carl D. Anderson in 1932 and named positrons, a portmanteau of positive electron. Although Dirac did not himself use the term antimatter, its use follows on naturally enough from antielectrons, antiprotons, etc. A complete periodic table of antimatter was envisaged by Charles Janet in 1929. The Feynman-Stueckelberg interpretation states that antimatter and antiparticles are regular particles traveling backward in time. Point number 3. Natural production. Positrons are produced naturally in beta plus decays of naturally occurring radioactive isotopes, for example, potassium-40, and in interactions of gamma quanta, emitted by radioactive nuclei, with matter. Antineutrinos are another kind of antiparticle created by natural radioactivity, beta decay. Many different kinds of antiparticles are also produced by, and contained in, cosmic rays. In January 2011, research by the American Astronomical Society discovered antimatter, positrons, originating above thunderstorm clouds. Positrons are produced in gamma-ray flashes created by electrons accelerated by strong electric fields in the clouds. Antiprotons have also been found to exist in the Van Allen belts around the Earth by the Pamela module. Antiparticles are also produced in any environment with a sufficiently high temperature, mean particle energy greater than the pair production threshold. It is hypothesized that during the period of baryogenesis, when the universe was extremely hot and dense, matter and antimatter were continually produced and annihilated. The presence of remaining matter, and absence of detectable remaining antimatter, is called baryon asymmetry. The exact mechanism which produced this asymmetry during baryogenesis remains an unsolved problem. One of the necessary conditions for this asymmetry is the violation of CP symmetry, which has been experimentally observed in the weak interaction. Recent observations indicate black holes and neutron stars produce vast amounts of positron electron plasma via the jets. Point number 4. Positrons. Positrons were reported in November 2008 to have been generated by Lawrence Livermore National Laboratory in larger numbers than by any previous synthetic process. A laser drove electrons through a gold target's nuclei, which caused the incoming electrons to emit energy quanta that decayed into both matter and antimatter. Positrons were detected at a higher rate and in greater density than ever previously detected in a laboratory. Previous experiments made smaller quantities of positrons using lasers and paper-thin targets. However, new simulations show that short, ultra-intense lasers and millimeter-thick gold are a far more effective source. Point number 5. Antiprotons, antineutrons, and antinuclei. The existence of the antiproton was experimentally confirmed in 1955 by University of California, Berkeley physicists Emilio Sager and Owen Chamberlain, for which they were awarded the 1959 Nobel Prize in Physics. An antiproton consists of two up antiquarks and one down antiquark. The properties of the antiproton that have been measured all match the corresponding properties of the proton, with the exception of the antiproton having opposite electric charge and magnetic moment from the proton. Shortly afterwards, in 1956, the antineutron was discovered in proton-proton collisions at the Positrons, Lawrence Berkeley National Laboratory, by Bruce Cork and colleagues. In addition to antibaryons, antinuclei consisting of multiple bound antiprotons and antineutrons have been created. These are typically produced at energies far too high to form antimatter atoms, with bound positrons in place of electrons. In 1965, a group of researchers led by Antonino Zertucci reported production of nuclei of antideuterium with the proton synchrotron at CERN at roughly the same time. Observations of antideuterium nuclei were reported by a group of American physicists at the alternating gradient synchrotron at Brookhaven National Laboratory. Point number 6. Antihelium. Antihelium-3 nuclei, 3He, were first observed in the 1970s in proton-nucleus collision experiments at the Institute for High-Energy Physics by Y. Prokoshkin's group, Provino near Moscow, USSR, and later created in nucleus-nucleus collision experiments. Nucleus-nucleus collisions produce antinuclei through the coalescence of antiprotons and antineutrons created in these reactions. In 2011, the STAR detector reported the observation of artificially created antihelium-4 nuclei, anti-alpha particles, 4He, from such collisions. Point number 7. Preservation. Antimatter cannot be stored in a container made of ordinary matter because antimatter reacts with any matter it touches, annihilating itself an unequal amount of the container. Antimatter in the form of charged particles can be contained by a combination of electric and magnetic fields, in a device called a penning trap. This device cannot, however, contain antimatter that consists of uncharged particles, for which atomic traps are used. In particular, such a trap may use the dipole moment, electric or magnetic, of the trap particles. At high vacuum, the matter or antimatter particles can be tracked and cooled with slightly off-resonant laser radiation using a magneto-optical trap or magnetic trap. Small particles can also be suspended with optical tweezers, using a highly focused laser beam. In 2011, CERN scientists were able to preserve antihydrogen for approximately 17 minutes. Point number 8. Cost. Scientists claim that antimatter is the costliest material to make. In 2006, Gerald Smith estimated $250 million could produce 10 milligrams of positrons equivalent to $25 billion per gram. In 1999, NASA gave a figure of $62.5 trillion per gram of antihydrogen. This is because production is difficult. Only very few antiprotons are produced in reactions in particle accelerators, and because there is higher demand for other uses of particle accelerators. According to CERN, it has cost a few hundred million Swiss francs to produce about 1/1000th of a gram, the amount used so far for particle/antiparticle collisions. In comparison, to produce the first atomic weapon, the cost of the Manhattan Project was estimated at $23 billion with inflation during 2007. Several studies funded by the NASA Institute for Advanced Concepts are exploring whether it might be possible to use magnetic scoops to collect the antimatter that occurs naturally in the Van Allen belt of the Earth, and ultimately, the belts of gas giants, like Jupiter, hopefully at a lower cost per gram. Point number 9. Uses. Medical. Matter-antimatter reactions have practical applications in medical imaging, such as positron emission tomography, PET. In positive beta decay, a nuclide loses surplus positive charge by emitting a positron. In the same event, a proton becomes a neutron, and a neutrino is also emitted. Nuclides with surplus positive charge are easily made in a cyclotron and are widely generated for medical use. Antiprotons have also been shown within laboratory experiments to have the potential to treat certain cancers, in a similar method currently used for ion-proton therapy. Point number 10. Can we obtain it from the space? During the Big Bang theory, the whole space would have been surrounded by equal matter and antimatter. But now we cannot find any antimatter in open space. It is still a very big mystery that where did the antimatter go? The researchers performed till now have not found antimatter in space, but if we find it in near future, then till would solve around 80% of the total world problems. So guys, this was all in this video. Meet you in next video. Thanks for watching. Bye bye.